Welcome back to your Dynamics of Rigid Bodies. Okay, so we are still on your Module 3, Kinetics of Particles. And then, of course, we have here your Unit 3, which is your Impulse and Momentum. And then, of course, these are your learning outcomes. Okay, so first is for you to develop the principles that relates impulse and momentum. And then second is for you to solve problems regarding these impulse momentum problems. Okay. And then lastly, for us to understand the concept of conservation of momentum. So let's first define what is momentum. Okay, so if we say momentum, that is the measure of mass in a motion. And that is just equivalent to the product of the mass times the velocity of any body. Okay, of any body that is in motion. So that's why, okay, for example, we are using this word momentum to define, let's say, a team. Okay, let's say a team of in sports. Okay, we use this word momentum. We will say that team is in momentum if they are winning successively because they are just like the success is moving forward. Okay, or there is a motion or there is a movement as a team. So again, momentum, that is, if we are now trying to define it technically, that is just the amount, or that is just the measure of mass in motion. So again, that is just the product of your mass times velocity. Okay, and of course your mass could be in kilograms or slugs if you are in English, and then of course your velocity will be meter per second, or that will be feet per second if that is in English units, and of course etc. If you are using different units, you will be having different, how, as long as those are just actually the mass times the velocity. So as you can see, kilograms, slugs are mass, meter per second and feet per second are velocities. So let's say p there, or small p, is will be our variable that will denote the momentum of body in motion. And again, that is just the product. So let's say m is the mass of the body and v is the velocity of the body, then p is equal to m times v. That is your momentum. Or again, if you will try to look at any other sources, there are other formulas for this, just like force over time. Actually, other books define your momentum as the time rate of force. Okay, time rate of force, or it is, if you say time rate of force, that is the force divided by a time. So that could also be the formula for momentum. But for this discussion, let's make use of the mass times the velocity. Okay, mass times the velocity. Or I'm sorry, a while ago that is force times time, not force divided by time. Okay, so as long as you will end up with the same unit as this, that is another formula for momentum. And then what is impulse? If we say impulse, okay, relating it to your momentum, the impulse is actually just the change in momentum due to an external force. Okay, so let's say you have there a body which is in motion, and then you will try to apply an external force. Okay, let's say, okay, you have there a ball which is initially rolling, so there is a motion, therefore there is a momentum, since of course we will expect that that ball has a mass. Okay, so originally that is in motion, that is rolling, and then you are going to push that one further, or you are going to apply an external force. What happens on the ball if you are going to apply a force directed to the original direction of motion? What happens is that the original ball which is rolling, that will now accelerate. Or if you try to apply an external force which is opposite the original direction of motion, that will now decelerate, or rather stop. If you will apply a bigger force, that will stop. But if you are going to apply together with the direction of motion, then that will accelerate the original body in motion. Okay, so again, impulse there, if we are talking about impulse, that is the measure of the change in momentum. Because again, what is momentum? Mass times velocity. Originally, that there is a mass, okay, and that is constant, of course, because nothing happened with the mass. We just applied an external force. So the mass there is constant, and the velocity changes, isn't it? So what happens is that the momentum initially is there, but once you apply an external force, it's either it will make your velocity bigger or smaller. Then you will expect that your final final momentum will be different from the initial. So that change between that final and initial is the impulse, okay? And that is due to the external force. Okay, impulse is the change in momentum due to an external force. External force, it is outside the body itself. So how do we get that one? So let's try to start with your Newton's second law of motion. Okay, that is again the F is equal to ma. That is coming from mass is equal to F over A, isn't it? So force is equal to mass times acceleration. You will try to break this, or let's try to change your acceleration, since actually that is the change of velocity with respect to time, isn't it? That is acceleration. So let's try to rewrite that one into that form. Acceleration, let's change that one into dv over dt. And then play around with this, dt cross multiply that one together with your force F. So this will be the result, F dt equals m dv. Now for us to have a formula, of course integrate for us to cancel the derivatives or these differentials here. So integrating both sides, your variable here is t, so of course your limits will be t, but we are considering the initial time to final time, so at time O and time F. So of course you are just considering here a range of time or time interval. And then of course integrating this other side, your variable here is v, because mass is constant. Let's consider that if you will apply an external force, it will not change the mass of the body in motion. But let's say if you will apply an external force, it will rather add a mass or subtract a mass, then that will be a different case. Your m is also a variable. But let's say, okay, let's simplify. Let's say that the mass is still the same. So again, after applying the external force, the mass is still the same. So let's say that is constant. Then integrating both sides, your variable here is v. So at time 0, of course, we will consider the initial velocity also. And at any time f, we will consider also the final velocity at that time. Okay. So again here, this will be your formula, integral of f dt from to to tf if, okay, f is a variable. If f is a variable, then you need to include that one in the integration, especially if your force is expressed in terms of time. So all you need to do is substitute that one, so that will become equation of time, then integrate with respect to time, and then of course apply your upper limit, lower limit. But if your force is constant, okay, if your force is constant, then you can actually bring that outside, so that integrating this one, this will just be tf minus to. Again, integral of dt is t, substitute upper limit, minus substitute your lower limit. So actually that is just tf minus to, or we can call that one as change in time, or that is actually your time interval. If your force is constant all throughout the application, okay, if you apply that force, and that will be constant, okay, it will not change. But there are some cases wherein if you will apply the force initially, at some time it will now change, okay. So the force is also variable, and that may be given as a function of time. So your force could be an equation in terms of t. So if that's the case, again, do not use this formula f times delta t, because again your f is variable, so you cannot just factor that one outside. So you need to include that one in the integration. But again, let's say that is constant, so f is equal just to the change of t, or tf minus to, or that is just the time interval that we are considering. And then of course in the other side, what happens, m is constant, again as I've said a while ago. What if that is constant? Okay, let's just factor it outside. And then integrating dv is v again, and then upper, which is vf, minus lower, which is vo. So distributing that one, you will have m vf minus m vo. What are these? If you'll try to go back to your momentum, that is just the mass times velocity. So in here you have two momentum, mass times the final velocity, and then mass times the initial velocity. So what does that mean? These are two different momentum. Okay, so that m times v sub o, that is the initial momentum, while your velocity is initial. And then your m times vf is your final momentum, since your velocity there is the final velocity. So again, initially you have the initial velocity. Once you apply a force, external force on the motion, it will change the velocity. Either it will add or it will subtract. So there will be a different final velocity, and multiply that one to the same mass, that will be your final momentum. So again, as we try to define your impulse as the change in momentum, that is actually where we ended up with this. MVF is your final momentum minus MVO is your initial momentum. So again, that is your change in momentum, which is supposedly your impulse. Therefore, that f delta t, or that f or integral of f dt from to to tf is actually your I. Let's call that as your I, which is your impulse. So again, impulse is integral of f dt, the force applied with the change of time from to to tf. Or again, this happens if your force is variable. But if your force is constant, that will just be simplified as f times change of time, or that is the time interval. Okay. Or if you have the momentum of final and then initial, all you need to do is subtract, then that is the impulse. Okay. That is the impulse. That is the effect of the external force you applied on the motion. So again, what is impulse? Since that is just a change in momentum, then that is still a unit of momentum. Okay. So it is still a unit of your momentum. And then if we will try to rearrange this impulse equation that we derived from your second Newton's law of motion, then you will end up with your impulse momentum equation. Okay, so from this one, let's say again, let's take it generally. Let's say that if there is any, it could be a constant or variable. So let's just take one as this. Let's just not write that as f delta t, since again we do not know if f is constant or not. So let's take it as is, and that impulse is equal to your change in momentum. So let's try to rearrange. I will transfer this MVO, or your initial momentum, on the other side. It will become plus. So leaving us your final momentum to be equal to initial plus your, what is this, impulse. Okay, so again, the final momentum is equal to your initial momentum plus impulse. Okay, or it could be minus if your impulse will subtract the momentum. So it depends on the cases again. If the impulse or the external force will magnify the velocity, then that will be plus impulse. But if it will subtract or it will decrease your velocity, then that will be minus impulse. Okay, so it depends. So again, you have here your definition, and then we have here your conservation of momentum. So let's just try to analyze what happens here in your impulse momentum equation if your resultant force is 0. Okay, so again, let's say you have there a body in motion, that is in motion. There are some cases wherein an external force applied is not just a single force. It could be a lot of forces which are acting at the same time on the body in motion. So you will expect you will be having there a lot of impulses, isn't it? Since we have there a lot of external forces. But if you will try to summate all these what do you call this one, all these external force, and you will end up with 0. Okay, if you will try to get the resultant of all this external force, and you will end up with 0, what do you expect here in the value of the impulse is that even if you have integration, but if your resultant f is 0, you will expect that the result of your impulse is also 0. Therefore, that leaves us your final velocity is still equal to your initial. So again, even if there are external forces applied on the body in motion, if they will actually just cancel out each other, then the motion will still be the same, or will still be constant all throughout. Okay, so the velocity initially is the same as the velocity final. At the same time, if of course nothing happens with the mass, then the momentum initially is the same as the momentum final. So again, what does that mean? If you will try to read my explanation here, okay, when the resultant f is 0, the impulse will also be 0. Therefore, the velocity of the body in motion will remain constant for the duration. and it will not accelerate, leaving the final momentum to be equal with the initial momentum. So that is what I'm saying. So if that's the case, if nothing happened, even if there are external forces, if nothing happened with your motion, again, because all of these cancelled with each other, then actually that confirms with your Newton's first law of motion, isn't it? What is your Newton's first law of motion? Uh, Again, if you try to recall your Newton's first law of motion is here. The absence of external forces on an object at rest remains at rest, and an object in motion continues in motion with a constant velocity. Okay, again, that confirms if your external forces that are acting together will eventually cancel out. So there is no resultant, net resultant that will affect the body in motion. So according to your first law of Newton, isn't it that if there is no external force that will affect your motion, the body originally which is in motion continues in motion with constant velocity. Isn't it that is your first law of Newton's? Okay, so again, so that is conservation of momentum. But of course, if there is now a resultant force F that will affect your body in motion, then you will expect that there will be a change in your momentum. Okay, so let's go back to our slide. Okay, so we have here now your, okay, this one. No, this. So that's why again we ended up with the final with the is equal to initial momentum. Okay, so let's try to have an example. So number one is determine the magnitude of the force acting on a highway bumper. Okay, if you say highway bumper, if you will try to look at this figure, those highway bumper are actually these that will serve as the safety precaution. If ever that there will be a vehicle that will lose control, that will serve as a barrier. Okay, so maybe you have noticed this one in between highways with the opposite flow of traffic. You can see this barrier if there is no fixed barrier. Okay, so we call that one highway bumper. So again, determine the magnitude of force acting on a highway bumper when a 5,000-pound car traveling at 60 miles per hour crashes against it. So let's say we have there a car that lost control and then it will bump or it will crash that highway bumper. And that car has a mass or has a weight of 5,000 pound. Okay, that is not slug, so unless it is given there to be pound mass. But again, we are not using that pound mass in solving technical problems. Okay, that is seldomly used. So what we are using is a pound force, and what is the mass of a pound force? That is slugs. Okay, so that 500-pound car is the weight. The 500 pound is 5,000 pound is the weight. Is traveling initially at 60 miles per hour and it crashes against the bumper. So what happens, of course, if let's say the bumper, but according to the problem, that the time it takes before the car brought to rest is 0.03 seconds. So let's say that the car is stick together with the bumper. They did not separate along the collision. So what happens there is after 0.30 seconds or with half your minute, that car which is initially 60 miles per hour will now be at rest. It will now stop. Okay, because again it crashes into your bumper. So what do you expect there? There is original body in motion, which is actually the car originally in motion at 60 mile per hour velocity. But since again it bumps or it crashes on a bumper, there will be already there a reaction of the bumper that will stop the car in motion, isn't it? So that is now an external force that is applied on the car, which is originally having a momentum or originally in motion. So again, the effect or the reaction of the bumper against the car will serve as the external force. So if you will try to draw the separate diagram, we will draw the diagram of the car, not the bumper, because we are referring here to the car as the original body in motion, originally body in motion. So that is this direction, okay, that is the original direction of motion, okay, going to the right. But once that will hit the bumper, of course, that will now stop after 0.30 seconds. But if you will try to look at this, your force is in pounds, yes. But again, you cannot end up with a pound force using a slug mass if your velocity or your acceleration is in feet per second squared or feet per second. I mean in miles per hour. You need to convert that one into feet per second because our gravity, if ever you need your gravity, is to be in feet per second squared. But actually, it doesn't. It has no effect of the gravity, or there is no effect of the friction. Why? Because in the first place, the car is in motion. So, and there is no given coefficient of kinetic friction here. So again, maybe the friction between the tire and the surface or the ground is negligible since again, the car is now in motion. And again, it did not apply the brake. It did not apply the brake. So in the first place, the car did not apply the brake. So there is no way that there will be a friction between the, there is a big friction between the tire and the surface. The resistance will be coming from the bumper because that is where the car crashes. So again, it did not apply the brake. It did not apply the brake. So there is no significance of the friction. And again, there is no given coefficient of kinetic friction. Okay, so however, if that is given, then you need to consider that one. But again, there is no given, so we will not consider the friction. So the only force, external force, that is now interfering in the motion of our mobile or on the car is the force that is coming from the bumper. So let's say that is the force. Of course, that will be against the motion because it will try to stop the car. So that will be opposite direction. Which is again, let's try to denote that one as F sub B. B stands for bumper, okay? That is the force, that is the reaction force of the bumper. So that will be opposite the direction of the car because it will try to stop the car. So what is our solution here is that the final momentum is equal to 0 since the car is brought to rest, isn't it? After the collision with that bumper, after 0.30 second, that 0.30 second is actually the time interval. Okay, that is the time interval. That is delta t. So delta t again is the time interval when the impulse happened. Okay, when the external force is applied on the motion. But it suddenly stopped at 0.30 seconds. So again, that is just the time interval that we will be considering. So again, after that time interval or at the end of that time interval 0.30 second, the car is brought to rest. So again, what do you expect? The velocity will now be 0. The final velocity is now 0. Therefore, if we will try to start with the equation of your impulse momentum, okay, final momentum is equal to initial momentum plus what happened by the way with your force of the or with the external force, that is just actually the force from your bumper, which is actually constant. Okay, it is not changing within that 0.30 second, and even if you will say it will change, that is just a matter of it is actually not 1 second, it is just point something second. So even if there's a change, then that will be negligible. Okay, or let's just take your f to be constant. So if that's the case, then I will not be using the integration. I will just use here that delta t. The delta t is actually just the change in time, or that is actually given as your 0.30 seconds. So if you will try to substitute your VF, even if we have there a mass, we can compute here actually the mass from your weight. You can divide your weight with your gravity, isn't it? Divide that one with your gravity. What is gravity in pound, in feet per second square? That is 32.2. So we can actually get the mass from this, but your final velocity is still 0. So that the final momentum will be 0. Again, why? Because again, the car will be at rest after 0.3 seconds. Now, if you try to look at the other side, we have there a mass, that is again your weight divided by the gravity times your initial velocity. We have an initial velocity because the car is initially moving at 60 miles per hour, but as I've said a while ago, convert that one to feet per second. So that will be ending with your 88 foot per second. Okay, conversion. All you need to do is convert your mile to feet and then hour into second. You will end up with exactly 88 feet per second. And then that is to be substituted here. And then of course, why is it that I made your formula minus FB times 0.03? Because again, your force F there is opposite the direction of motion. So again, we need to follow your sign convention. So the car is initially moving, going to the right, but of course, it will be stopped by the bumper. So again, your reaction F sub B is opposite the motion. So that is a negative. Therefore, this will make it minus F sub B, and your change of time or your time interval is 0.3 seconds. So substitute that one. Then you have your equation with only F sub B to be the unknown. This will go positive. Divide both sides by 0.03. You will end up with 45,548.65 pounds. So what does that mean? That is the force that is coming from the bumper that will resist the car originally in motion, so that will stop after 0.30 seconds. Okay, so that is the magnitude of the force that we are trying to find. Okay, so that is your example number 1. Let's try to have one more. So a pitcher throws a fastball that is moving at a speed of 90 miles per hour. Okay, so we are referring here to a sports which is the baseball. Okay, baseball. So the pitcher will throw a fastball. So let's consider the throw of the pitcher to be in horizontal. Okay, let's say that is a strike in horizontal. And initially, okay, we will follow since this is this figure here is given actually by the problem. So let's just follow. So even if it did not states there that your original motion is horizontal, since that is given in the figure, then we will consider it horizontal. So the initial velocity of that ball, which is thrown by the pitcher, is 90 miles per hour. Okay, that is your visible. Let's write that, convert that one again into feet per second. So that is equivalent to 132 feet per second exactly. And the batter hits the ball in the direction shown. So again, this is given by the figure. So that is the direction how the batter hit the ball that is pitched. So again, it hits the ball that way so that the ball will bounce back within this 35 degrees direction. And the ball will now leave the bat at a speed of 175 miles per hour. So now, from 90 miles per hour, of course, because there is a motion, or there is also your bat is in motion, which is maybe a very, very strong force applied from the bat, then that will magnify your velocity but opposite direction. Almost opposite, because not totally opposite, since that is inclined. And that will be going at 30 degrees from the horizontal. Okay, and if the bat and the ball are in contact for 0.020 seconds, so it is just a glimpse of time for the ball and the bat to be in contact, so that is your delta t. Okay, determine the average impulse force exerted on the ball by the batter during the impact. Okay, the ball weighs 0.25 pounds. So I'm sorry, this should be weight. This should be weight. Let's just change that one. Okay, so again, we just changed that one to weight, since that is weights. It says there weighs, and actually you can see that in your pounds. That is a pound force. Okay, so again, that is the weight of the ball, 0.25 pounds. And again, what we are trying to find here is the average impulse force, or that is just the force applied by the batter. Okay, that is the batter. The force applied by the batter, so that ball, initially 90 miles per hour, will now be 175 miles per hour given that direction 35 degrees. So what do you expect is that the batter also applied this bat, or the batting force, or the force, in an inclined manner, so that this ball will bounce back at an inclined manner. But it is not of course given that the butter also applied the force at 35 degrees from below. We do not know that one. We will prove that one if that is the case or not. So again, but we will not assume, of course, that the butter or the force applied by the butter is the same angle from below. Okay, so we will prove that one later on. So that's the case. We have the weight to be 0.25 pounds and your initial velocity of the ball to be 90 miles per hour. Converting that to feet per second is 132 exactly. And the final velocity is 175 miles per hour, which is to be converted in feet per second is equivalent to 770 over 3. We will use that fraction, we will use the exact value since we will be needing that one. We will be using that one in the solution. So I'd rather use the whole number. And then the time of contact, or that is actually the time of the impulse, is just 0.02 seconds. If we say time of contact or time of impulse, that is the time when the external force is applied before it ended up moving on the opposite direction. Because once that is now far from the bat, then the external force has nothing to do with that already. So only the external force applied on the original motion at 0.02 seconds. So that is what we will be considering as the delta t. Since again, the force applied by the butter is constant, then we can just make use of the formula F, or of the impulse to be F times delta t. We will not be using the integration since again your force is not given to be variable. Okay, so however, the point here is that, okay, if we will try to separate the free body diagram of the ball here below, since again that is the original body in motion, the ball. So this is the original direction of motion going to the right also, and that is perfectly horizontal. So let's say I will consider that an axis from the point of impulse or the point of contact where the ball starts to change direction. I will consider the x and y axis there, wherein x is the horizontal, y is the vertical, since that is of course perfectly horizontal and vertical. Then as you can see, we cannot just summate the forces horizontally, since now the final velocity is as an inclined velocity from the horizontal. Or what does that mean is that the motion after the impulse is now different from the original direction. And that is inclined, that is not perfectly horizontal, so we need to consider the components of forces. Since again you will not just follow horizontal or that inclined, since again we need to break this down into components. So if I will try to look at the external force acting on the ball, actually that is just the force applied by the bat. And again, what do you expect? The force applied by the bat is going that way. Why? So that the ball will go that direction. But it is not again given to be the same angle from the horizontal. So let's try to figure that out later on. So what we know is that is inclined going to the left and going up. So if I will break this down into components, horizontally vertical or x and y components, then this is, okay, by the way, there should be theta there. I forgot to put in your first slide, but there should be theta here. Okay, so let's. Okay, so again, this one, I just put there the theta. So theta again, since we do not know if that is exactly 35 degrees or not, so let's just say that is unknown theta. So again, we need to break down the motion horizontally and vertically. So that inclined force that is actually coming from the bat that is applied in your ball is to be break down into x and y components. So what is your f sub bx? That is actually the adjacent to your angle, so that is cosine of f sub b. And then that fby, if you will transfer here, that is the opposite of your angle theta, so that will be your sine. fby is your sine of f sub b. Okay, so let's try to focus on the motion along x-axis. We will consider first the horizontal motion. So again, we will be following, since there is again external force applied on body in motion, so we will start with the impulse momentum equation. So final momentum is equivalent to the initial momentum plus the impulse. Okay, So mass times final velocity along x. Okay, final velocity along x. So what is the final velocity? That is 175, which is converted into 770 over 3. And your mass is coming from the weight divided by gravity. So that is your 0.25 divided by 32.2. That is the mass coming from the weight. And then your final velocity along x, or horizontal final velocity, is actually, break this down into horizontal. So again, the horizontal is the one attached with your angle 35 degrees. So your horizontal component of final velocity is cosine. However, that is negative. Why? Because the original motion is going to the right, but your final velocity is against it. It will now be going to the left. That is the horizontal component of your VF. So that is a negative 770 over 3. And then again, getting the component, that is cosine 35. Again, why cosine? Because that is adjacent to your angle 35. And then on the other side, the initial momentum, that is the mass, which is the same. And then times the initial velocity horizontal, which is, if you will try to look at the initial velocity, that is plainly horizontal. So we do not need to break this down into components. That is just converted into feet per second, equal to 132. Positive. Why? The same direction as your DOM. And then your FB sub x, we put that as negative since that is against your direction of motion, times the delta t, which is given to be 0.020 or 0.02 seconds. Okay, so this is just a number, and that is just a number. Calculating your f sub bx, since that is the only unknown in this equation, you will end up with 132.86. So that is actually the horizontal component of the force coming from the butt. Okay, by the way, that sub b means butt. Okay, so that is the force from the butt. That is the horizontal component of the force from the butt. Now let's try to proceed with your vertical or along y-axis. So since there is no, we cannot decide actually, since the original motion is perfectly horizontal, so there is no original motion vertically. So let's try to assume, let's say that going up is positive. It's up to you. You can assume actually going down as positive. It's up to you. It doesn't matter. Since again, initially there is no original direction vertically, since that is perfectly horizontal. Okay, so let's say going up is positive. So the same, your impulse momentum equation. So your mass is the same, but your final velocity y, instead a while ago is cosine, and that is negative, isn't it? But this time, assuming that going up is positive, and your final velocity is going up, so that is now positive, 770 over 3. And that is, if you will try to get the component of the velocity vertically, that is opposite 35, so that is now sine 35 degrees. And then of course your mass times your initial. But again, as I've said a while ago, the initial velocity is perfectly horizontal, so there is no initial vertical velocity. So that is 0. Therefore, this is useless. So there is no initial momentum vertically. But we have an impulse, isn't it? Because your force applied from the butt is inclined. So there is a vertical component of that. And okay, wait. That should also be positive. I'm sorry. Okay, so again, that should be plus. I just changed it to plus. Why? Because again, we assume that going up is positive. Therefore, your velocity final there is positive. So this is positive. And then, of course, our y component of our f sub b is going up. So that is also positive. Times your delta t, which is the same, 0.02. The impulse time horizontally is 0.02, and that is the same impulse time with your vertical. Okay? Since we just break this down into x and y component. Therefore, this is just a number that is useless. So all you need to do is get this value divided by 0.02 to get that f sub b. Okay, so that is f sub by. Okay, so getting your f sub by, we will end up with 57.15 pounds. Then what do we need is, of course, the impulse force, or the force that is coming from the butt. Okay, that is applied to the ball. So that is your f sub b. We do not actually need that f sub bx, f sub by. We only need that one to get your f sub b, since that is the unknown in the problem. So, of course, by Pythagorean theorem, since isn't it, if you'll try to relate this one as right triangle, f sub bx, f sub by are the legs of your right triangle, and getting that f sub b is by Pythagorean theorem. Okay, that is again from your statics. So Pythagorean theorem, f sub bx squared plus f sub by squared, get the square root, that is your f sub b, or your resultant, which is 144.63 pounds. Okay, that is of course not just the unknown there. Even if it is not given, we need to check what is the angle of the application of that force from the butt, or that means what is the angle of the application of the butt, okay, of the heat of the butt to your bone. It is again, as I've said, it is not automatically 35 since your ball is originally in motion. Okay, if that ball is originally at rest and you will try to hit that one, the angle of application of force is the same as the direction of motion. But again, that is initially in motion. Again, initially your ball is in motion and your butt is applied, before your butt is applied. So you will not expect that the angle in the incident angle is the same as the original angle of application. So we will check that one actually by getting, since we have there the components of your right triangle of your f sub b, you can get the arc tangent, isn't it? Arc tangent, since your f sub by will be transferred here, that is opposite, and f sub bx is adjacent. So tangent theta is opposite adjacent. F sub by over f sub bx, get the arc tangent of that to get the theta, that is 23.31. So we have proven that that is not the same angle as this, because again, initially your ball is in motion. It is not at rest. So you will expect that the angle, the original angle of application of the force is not the same as the result angle of motion. So that's it. So what does that mean? So in order for us to have that 175 mile per hour, which is directed 135 degrees from horizontal, we need to apply a force which is 144.63, or the batter should apply that force 144.63 pound at an angle of 23.31 from the horizontal. Okay, so that's it. So that is how we answered your example number 2. Okay, so let me just give you a hint. When do we use your impulse momentum? Actually, if we are just relating here, we are just still in your kinetics. So we are just relating the force, the force that is acting on a body in motion. So again, if you are just referring to the purely motion, that is the acceleration, time, distance, velocity, those are just kinematics. But once you will now consider the force that is actually causing the motion, or that will affect the motion, that will now be your kinetics. And isn't it, we have these solutions in your kinetics, wherein second law of motion, force is equal to mass acceleration, and then you have here your work and energy and power, and we have also this one, impulse and momentum. Okay, so I will just give you a hint here. If you are just referring here to force, relating the force on the motion with the mass of the body and its acceleration, that is simple as second Newton's law of motion. But if you are now relating it to the energy, okay, there is a change of energy, or there is an energy, power, and work related to the problem with the kinematics or with the motion, then you need to use these equations that we discussed in your unit 2. But if you have here a change in speed or change in momentum, because maybe there is now originally in motion and you suddenly apply there an external force, then you will expect there a change in momentum or an impulse. Then you need to make use the impulse momentum equation to solve whatever is being solved there, any problem. Okay, so that is for this topic. So again, let's just review some concepts, some of the concepts that we discussed. Momentum is just the measure of mass in the motion. So that is just equivalent to the mass times your velocity. Okay, so impulse is just a change in your momentum due to external force. So again, the motion will never ever change unless there is an external force applied. That is the first law of Newton. Okay, the body in motion will remain in motion, or the body at rest will remain at rest unless acted upon by an outside force, or that is external force. And final is that when the external resultant force is zero, the impulse is also zero, leaving the initial and final momentum to be zero. Okay, so as I've said in your law of conservation of momentum, if you have a body in motion and there are a lot of forces, external force that will act at the same time, but if you'll try to compute the resultant, there is no remaining resultant that will affect the motion, then the motion will still be constant, even if there is an external force. Okay? So these are the important concepts in your impulse and momentum. So if you have any question, comment it below the video. So thank you very much for watching.